people who attended previous classes before. I see a couple of newcomers, so I will also still do another intro about the class. So for anyone who are here, who have attended previous classes, this is the 8th one, and kudos to people who have been keeping coming to these classes. As the materials are now getting harder, I really appreciate that people are staying this and be able to keep exploring quantum computing together. For people who just joined today, we have this Sunday class, which is held by Hackaday, and we have everything that's posted on the Hackaday project. I have the link here. For past recordings and slides, you can find there, and I also make announcements there about new features and projects that Microsoft does. And my colleagues do. They also have very interesting fun projects, which I also promote there. So every Sunday, we will do a 30-minute presentation of one topic. We were not trying to overwhelm people with all things quantum. So we got to do just one concept, and we discuss it for 30 minutes. And we have questions at the end. People can ask in the chat, or they can unmute themselves to ask questions. We have some references that we've been using. One is the Microsoft Q# documentation. That's where all the explanations of Q#, the language, how do you code, how do you use quantum computing, you can find there. We also use the quantum katas, which is a very nice set of exercises. You can familiarize yourself to practice on these topics that we discuss. And before I forget, I think for next class, I would do a recap for previous topics, as the content now getting more advanced. Some of the new people may find it difficult to follow, even though there are past recordings. So I'm planning to do a longer session next week, and then probably through a different channel. So pay attention to the Hackaday project. How this will be broadcasted will be announced there. Last class, we talked about Deutsch's algorithm and Deutsch-Holzer algorithm, and I showed this that we have a list of interesting and historically discussed algorithms that we may discuss in this class. So today we're going to talk about Gruber's algorithm, which is, in my opinion, very funky, very cool, and is an algorithm that helps us search any particular item in a unordered list. But before we go there, I remember this slide from last class. I hand sketched this interaction for Deutsch's algorithm. I think we want to do a recap here, because there are some concepts that we will reuse today. And also, I think it was quite fast last time when I went through this, so I would like to walk people through the basic again for Deutsch's algorithm, which is a simplified version of Deutsch-Holzer algorithm. And what it does is having a gate, H gate for the input qubit, and then we have a output qubit Y. But why are we calling this input and output is because when we set up this algorithm, we introduce how we would do it classically. And classically, the input is this one input with a function which will then equal to the output Y. The function f of x is what we want to figure out. But then when we want to set up the same problem with a quantum algorithm, we have to change the order, the way we construct them. And we will put this is a oracle, also known as a black box, where you put into a quantum algorithm. And what this does is that given the nature of f of x, we would have this algorithm run once and be able to know what f of x is in terms of whether it is a balanced function or it is a constant function. I noticed some typos here. I will change them after the class. And if you still remember this circuit diagram, and I also made a more complicated Deutsch-Hose algorithm, that basically what we're doing here with the y is to have a negative sign introduced. So if you start with 0, having an x and an h, we'll put it in a superposition that has this negative sign here. And this negative sign is used throughout the algorithm to be carried over until the end. There are 4 states in superposition, but these negative sign, the effect of this negative sign would create a destructive interference for the plus states, leaving your system with only the negative states. And then when you do a measurement, you will get from the minus, you will get 1 after the h and the measurement there. This is how they will behave with a balanced setup when you are entangling these 2 qubits. But if you don't entangle these 2 qubits, this negative sign would not have any effect, and it would just not interact with this other qubit, and it would pass, both of them will pass straight through without doing anything. And then in that case, you get a 0 here, and that's when your f of x is a constant function. So all I'm doing here, I'm just trying to show you the power of this negative sign carried through this whole circuit here. So in Deutsch's algorithm or Deutsch-Hose algorithm, we've seen how this negative amplitude can be used to do a destructive interference. Next, we're gonna see how we can even use the negative amplitude to enhance the signal that we want to find. This is the Gruer's algorithm. Is introduced by Love Gruver, who is an Indian-American computer scientist. This is how the circuit looks like. It's a little more complicated than the Deutsch-Hose algorithm, but again, it also has an oracle in it, but then an additional box. We're gonna see what these 2 things do. And then the rest of them are the same as the Deutsch's Hose algorithm. The setup looks like this. When you're thinking about it classically, it would have some inputs, which are labeled as x, and then it goes through a function and then gives you an output. If you draw a truth table, so this is basically what this algorithm can do, is there are only 2 outcomes for the outputs, and all of them will be 0, but only one of them will be 1. And this is an unordered list. It could be, there could be a 1 anywhere on this list. So in this case here, we just arbitrarily give 1 to the input 1 and 0 here. And this is what Groover's algorithm trying to find is to figure out which of this input is given us this 1 here. And that's to figure out the nature of f of x. And I already showed the oracles in earlier pages. So if we want to change this classical setup into a quantum algorithm setup, then we would need to have an oracle like this. And then you have the inputs and 1 output at the very bottom. So in Groover's algorithm, we need some oracles or a black box that could capture these truth tables. So say if we have a black box for 110 for this truth table, what it has inside is basically all these input qubits being a control for the last target qubit, which is our output y. And what does this do? What does it control all of these, the other inputs being the control for the last qubit? It is very similar to what we learned in CNOT, where remember when we have a CNOT gate, the first qubit is our control, second qubit is target, and then the matrix will look like 1, 1, but then the other 2 flip. So then if we have additional qubits being the control, your matrix will be just all the way 0, but then the last one will be a flip. So by the way, this is Toffoli gate. I didn't discuss last time, but now I'm showing you is a control CNOT gate. And then you can have a lot more. You can have more control qubits. All it does is to have a really big matrix with all of the diagonal being 0, being 1, except the very last bit. So now when you have 4 qubits in the system, if the first 3 are the control, then your matrix would be just one more element added. So that tells us if all of the, it will only affect the last qubit if all of the above qubits are 1. Are 1. When any of them is 0, it wouldn't do anything to the last qubit. It would be intact. So then if your x012 is 110, you need to flip the last qubit. So that's why there's a X gate here, so that it will become 1 in order to affect this qubit. And then after the black box, it will just flip it back. This is Groover's black box or oracle for 110. But then you can have other options, like you could have, this is 0110, but then you could have, say, 010. And all you do is to just add the X gates to those qubits that were originally zeros. But if you don't have any 0, if you're beginning with 111, then you don't have to have any X gate. So that's it. That's oracle that you need in the Groover's algorithm. But then the complete Groover's algorithm looks like this. It has that oracle, but it also has an additional set of gates. And we're gonna show you this later, but then let's just look at it step by step. What is this whole circuit doing? So we always start our circuits with initialized qubits to be zeros. So then when you are starting up, even though you have 3 qubits in your system, and you could have all these 8 states in superposition, but then the first one, when you start with, only the 0, 0, 0 will have the amplitude, and it will be 1. And we're using n equal to 3 as just a proof of concept. In real case, n could be really large, but 3 is a good number. It's not too few. If only 2, it doesn't show much, but it's not too large. Otherwise, we can't really show things nicely like this. So we just use n equals to 3. So that's your all the possible states. So then when you apply the H gates, you would then equalize all of the probabilities for all these gates. So all of them will be then in the superposition of zeros and ones. So in total, you have all these 8 states in equal probability. So that's what this initial part does. And I haven't talked about X, the X and H gate on the last qubit. That's very simple. That's what we saw earlier in the Deutsch's algorithm. So all you do with this last qubit is introducing this negative sign. So what happens when you have this negative sign going through this oracle here? Remember that if these first 3 qubits are 1, then it will flip the last qubit. And that negative sign gets carried to whatever this black box is set up for. So in this case, this black box is for 1, 0, 1. So that's why we have this X gate for the initial 0 qubit. So this negative sign gets used to make this particular amplitude negative. That's really interesting. And what happens next is kind of repeating this, but then using a slightly different setup. So look at this other part here. It looks very similar to this one, but then it has X gates for all of the qubits, and also having an X gate in front of the last qubit. So just ignore anything earlier, ignore everything else. Just look at this part. What does this do is that, same again, only when these 3 qubits becomes 1, it would make an effect on the last qubit. So this requires that if you want to have these X gates in front of them, then they better be zeros before coming into this box. Then they can apply to here. So if you do the math, I showed it here. I reduced all of the math for the other parts, but this part I wanted to show that, remember earlier what happens to this one is it makes that 101 state negative. So this does the same thing. It makes whatever state that is 000 negative. So you have this negative amplitudes introduced, but then this X gate for the last qubit would do a flip. So everything will be flipped. So initially, this 000 will have the negative amplitude, but then after this flip comes in, this one will become positive, and all of the rest will become negative, all of the other possibilities. So this box actually just does exactly the same thing as this one. It flips the sign for the one that initially would have zeros in them. So this one flipped for 1, 0, 1. This one flipped for 0, 0, 0. But then this x here, then reverse it, makes everything else negative, but 0, 0, 0 positive. Okay, so that's what this box does. But then we have all these H gates around. What do they do? Interestingly, when I showed you a few sessions ago about H gate, there's something I left out, I didn't mention. So I explained that the H gate is changing your 0 to plus. This is the block sphere. And then from 1 to minus. And so one way to think about it is that if you start with these 0 or 1 states, these are like classical states, but then applying an H gate can put them into superposition in those middle states. So then that is showing you some quantum state with superposition. So that's what I discussed before. But what I left out is that you can also think about it as swapping x's for your qubit. So initially you have these 0 and 1 as your bases, but due to symmetry here, there's no reason you can't have the plus and minus be your bases. So doing an H gate to your qubits has an effect to swap your qubit's basis to its perpendicular axis. But this is only for one qubit. When you have a more complex multiple qubits, then you have to think about this multi-dimensional space beyond 3 dimensions. That's not easy to think about, but when you get used to it, you realize all what the H gate does is to flip whatever input by a perpendicular angle. So when you have a 3-qubit system, you will have all these 8 bases, and they all come in with an amplitude. And what these H gates do is that it finds where the mean value is, and then flip, using the mean value, all of the amplitudes with it. So in a way, this 1 qubit block sphere does that already, is flipping from this axis to this axis. But then when you have multiple states, you're finding where the middle ground is, which is all the mean value of all the amplitudes, and then you do a flip. This is really cool. So what happens is that all of the other amplitudes got smaller here, but then that one that was previously negative got even larger. So it picks out the signal from the state the black box was set up for. And there's other way to represent it. So previously I was showing you only the amplitudes, but then you can also use, so block sphere is a way for you to think about this 3-dimensional geometry, but now we have 8 dimensions. We can't really think about real geometry there, but we can still use arrows to show the same thing. So is another way to show you that previously your if your basis was the normal 0 states, then when you do a flip, it is reversing along this axis. But then when you do an H gate, it could change your basis to a completely different, sorry, this one here, completely different vector. So then when you do a flip, it is going from here to there. And that one there is the answer you want to get. So when you're doing this kind of flip, this arrow is approaching this answer more and more. So if you do it again, you can flip along this axis and put this arrow here, but then do another flip with this axis, then your arrow would end up there, so even closer to the answer. So this is what the next few steps do, is that they do a repeat. They iterate between these two boxes. So if you do that one again, it puts this amplitude to negative again. And you do this reflection over mean box, it will make the other ones even make them negative, but then make this huge. So imagine, so now that we finish our circuit basically, but then this is very easy to show with 3 qubits, but imagine you have even more qubits. You will need more iterations to get this peak higher and higher. And yeah, so that's what I already showed. So that's how Groover's algorithm does the search. The advantage of it is that it becomes more efficient than a classical algorithm. So you think about how will we do this classically? If we have a list and to find which function gives us the 1, we have to check every single one of them. Unless if you're lucky, the first one will have the 1, then you will find it in 1 step. But if you're unlucky, it might be the last input. So you would do 2 to the n times classically. But then Groover's would shorten it to the square root of 2 to the n. So it's actually easy to prove this if you use that vector arrow notation. There's actually a pretty straightforward proof on Wikipedia, so you can use that. So that's why I'm not showing here. It's quite well explained. There's so many different ways of explaining Groover's algorithm. So I aim to be the one that uses cartoon to explain it. So if you want to find other ways to do it, there are so many online. And in fact, I'm going to point you to some of the really useful exercises that we have in the katas. And I think because Groover's algorithm is so funky, and I think it's really interesting to try them by hand. So we probably should do another class just to code and to express Groover's algorithm. We actually have several different ways to practice and get better intuition for Groover's. On the katas, we have this building your Groover's algorithm from scratch, which is this link here. So that is showing you like what I did, taking apart the circuit and showing you each step, applying different gates and building up the black box. This is one way to start from scratch, but we also have some applications of Groover's algorithm and some interesting using plot to visualize it. But we also have a fun repository from my colleague Maria, who did a decorating Christmas tree using Groover's search. This is out of season, but this was written during Christmas time, so it was really nice. Okay, so I'm finished with the Groover's algorithm for today. I want to point people to this very exciting event that's coming up next week, which is Microsoft Build. It's our developer event, and this year we are all online and it's all free to attend. So we have several quantum talks from my colleagues at different times in order to show this to people from different time zones. So there are some repeats here. If you register there, you will be able to find the schedule and add them to your calendar. So these are the quantum talks I would love you guys to look at, and we also gonna do some really exciting announcements, including the work that I've been working on that we're gonna launch during build. So make sure that you watch these talks and follow these 2 Twitter accounts. They will make really cool announcements that you would like to know. Okay, so just a reminder that you can still submit your katas. So now we have discussed Deutsch's algorithm, Deutsch-Hose, Groover's algorithm. So you can pick some of these more advanced topics and do katas, but feel free to walk through some of the earlier ones that's more basic and follow these steps and you will get a vector graphic where you can print anything. Someone who finished the katas got the certificate from me and he printed on a mug, which looks really nice. And of course, we have this history quizzes. You can also participate and get the certificate too, which is the out-of-the-box thinker certificate. And we're probably gonna come up with more. Okay, so this is for today. Any questions? Okay, I can see the chat here. Yep, Taro, thank you for posting the build link. There's a typo on the complexity on Groover's algorithm. Could be, I need to check again. What do you think that should have been? So I think it's just for linear search in the regular. That's right. Yeah. Oh wait. Yeah. Let me double check. That's what I originally thought, and then I thought it was 2 to the n, but I would double check. The slides will be available on Hackaday.
So for linear search in regular computers, it's just ON. You have to visit each element at least one time, or that's going to be your average.
Yeah.
So, okay. So yeah, I think maybe it's square root n, but I'm not entirely sure. So for Groover, I mean.
Yeah, it's not square root of n. I originally thought it was n, but then I got confused, and let me double check.
All right, cool.
Yeah.
Thanks.
And I will correct it on the slides if it's wrong. I need to scroll all the way up to see the first questions. Okay. So slow today. Okay, so Benjamin asked, okay, Aaron first said, an oracle is someone who predicts the outcome of their own input into the system. In classical Greek history, yeah, thank you. That system is someone's life. And the input is a wise in which the outcome is known. Yeah. That's why I put that angel there in the cartoon. Barry says, not sure that this is where the quantum computing terminology. Yeah, so that's why actually in the second certificate, I asked people to look, why are we using oracle in quantum language? It's kind of strange. I think the question is how it started. Yeah, the history, why. In theory of computation, using an oracle gives you a solution to an unsolvable problem, but then you get problems that are even higher level of unsolvability. Yeah. Eris says, it's not a popular definition, but the guess fits every mention. Yeah. Once you know what oracle is, it kind of makes sense, but when you first look at it, it's like, why do they call it oracle? Yeah. Okay. I often hear Barry says Groover associated with database searches. Is there any truth to that? I read the post that is not correct. It is used for database search. And I think there's also applications in cryptography. And we can all look into that. I haven't quite got there yet. Taro says Groover is square root of n. Okay, so I am conflicted now. I actually have seen different complexity proofs that has different approximate order of how many iterations we should do for Groover. So I actually initially made a mistake. Well, I thought it was a mistake that is square root of n, but then I thought it should be square root of 2 to the n. I've definitely seen both around, so I think I should dig deeper on why there are different interpretation to that. And also, it might give us some more sense if we do some coding exercise at some point with Q#. I think that could also help us see. Complexity of Groover depends on what you define as n. Yeah, so thanks, Barry. Would you mind elaborate on that? Because I'm not quite sure how we have different definitions. And feel free to unmute. So Barry says if n is the number of qubits, is square root 2 to the n, okay? If n is number of states, is, oh, okay. Okay, that's where I made a mistake. Okay. Yeah, so I originally was using n as number of states. There are 8 states. But then if there are qubits, is 2 to the n, correct? Yes, thank you. So, and it checks out is the same. 2 to the n for 3 qubits is 8. So Taro says, okay. Yeah, okay. Thanks, everybody. This is clarifying. And let's see, is there still another mistake somewhere? Oh, in terms of classical. Okay, yeah. So classical is 2 to the, yeah, I think just now we just talked about classical actually. So just now it was, we were talking about 2 to the n, where n is the number of qubits. If we're talking about states classically, it will be n times. That makes sense. And then you can try to prove the Groover's complexity using this angular method. Another question, is there any intuitive way to describe why Groover's operations achieve reflection about the mean? So that's what I think is already intuitive. I could try to show you another way if it doesn't add more confusion. So I have a written version, which me and my colleague wrote. Let me try to share the screen with you. Okay, so okay, I'm sharing a Word document. It's very mathematical, but we can skip the derivation. So if you have the patience, you could try to derive everything mathematically, and that actually is really useful. So then you can translate the math into more figurative ways. So let me see where to start. This is to prove the iteration. Okay, and this part is the initializing. So it's really exactly like when you have the basis being zeros, then you will flip with your normal basis, like 0 and 1. But if you have a H gate that changes your basis, then you would flip over that basis. Okay, so if we had a state 0, 0, 0, and then we can label it with arrow, but keep in mind that this is really a simplification of the space, because really is an 8-dimensional space, but we have to represent it in the 3-dimensional space because we're humans. So we have, there are a lot other dimensions we're not drawing here. So what H3H, so doing an H gate to each qubit does is putting all of them into a superposition of 8 possible states. And then represent that vector with this yellow vector here. And then you take an arbitrary state and you can just label it with some arbitrary arrow. You can do a reflection over the 0, 0, 0 axis, which was your original axis. So it flips over to that side. That is what's happening when you're keeping the 0, 0, 0 as your basis. But if you apply the 3H gate to all of them, you can expand the matrices, you can do all this, and then write out all of the elements. Then you are changing the original basis to a basis that is perpendicular to your original basis. Okay, so here is what we do. So remember we had that yellow arrow earlier? When you have the 3H gate on 0, 0, 0, you produce this arrow here. An arbitrary state is there. If your black box is 0, 0, 0, your basis is 0, 0, 0. So your original arrow is flipping with 0, 0, 0 as your axis. So this is flipping over the original basis. And that's what the first black box does.
Can you hear me?
Yes, I can hear you.
Finally, I figured out how to get the right mic going. Can you share a link to that document?
Yeah, we haven't published this yet, so it's not yet ready to be shared. But I wanted to show this arrow way of seeing what's happening. But at some point we're gonna have this public, and then you can use it. So that's why I was hesitant to really show this, because I don't know if it's really helping you to see it, or
It's just tough to absorb it in this fashion.
I agree. Yeah.
Without being able to spend a little time with it.
Yeah, so my recommendation here is, so what we did here is really, we had to write out the math and then represent them using these arrows. And then we see that it is first flipping with this as your basis, but later on, when the mean comes in, you're flipping around the yellow arrows. So we couldn't have got here until we really tried representing the math, and then in retrospect, it made a lot of sense. So what I would recommend you do is to forget about 3 states, 3 qubits. Just use a black block sphere and just see the symmetry in it to see what the H gate does to just a single qubit. Then you can gradually add more qubits and try to imagine in a multi-dimensional space where you're really just changing the basis to a different axis. And then whatever operation you were doing before would then have a different basis that is perpendicular to your previous one. So I think that's where you could get started. But I think intuitively, really, that you can visualize the first black box, the Grover's black box, and then you can see, okay, wherever we have an X gate, we would have the signal picked out of that. Wherever we have X state, we would have a 0. So this box picks out that signal. And then what the reflection over mean is that it already determined that it would have the 0, 0, 0 as that state for you to pick out. And what the H gates do are finding out what the overall mean amplitude is, and then do a flip over. So I think you will have a lot more intuition probably the 3rd time you go through Grover's algorithm. And I think a good way to do it is to use some of these katas to try to go over Grover's algorithm in several different ways. And this first kata here is actually telling you quite a few links where you can go to and find some of the existing, this need to refresh, published papers. So this exercise points you to several different lectures. You should take a look at them, and all of them explain Grover slightly differently. And most of them require some previous knowledge in mathematical proof. But then, so if the math gets too much, just think back about today's lecture using mostly graphical ways, and then go back to these lecture notes that would help you reinforce your understanding. Is there any other question? So hopefully that document we will be able to share at some point. So just right now is not public yet.
If it becomes available during the run of these courses, then it would be great if you could announce that.
Yes, definitely. Yeah, I will definitely announce it there. Another question. Okay, Bob asked, can the Oracle black box be implemented in a way that you don't need to know the answer to implement it? Having trouble imagining a practical interface from the Oracle implemented with qubits and classical source like a database. Yeah, so first of all, the katas would really help you get the real feel of it. And then because they're black boxes, we don't, only when you're setting up your black boxes, you know what they are. But when you're really running this algorithm, you just use a generic black box. And yeah, just I think using those coding exercises will really help you do that. Aaron, I'm not familiar with principal component analysis. Would you like to explain? We can leave that later too. Probably having some problem with his microphone. Okay, so with a little overtime again, thanks everyone for coming. And next class, I will do a recap. Okay, Aaron answers, basically finding a pair of axes that maximizes the breadth and minimizes the orthogonal breadth so that you can sum the vector magnitudes of the maximal axis. Yeah, I think I know what you're saying there. Okay, thanks, Aaron. Okay, thank you, everybody. We'll see you next time.
Thank you.
Yeah, thank you.
Thanks as always.
Thank you. Need to turn off the recording. It's really laggy, Teams. It's a new interface, I think. Stop.